So we're talking about the chemical context of life. So in the chemical context of life, oftentimes students are disheartened because you sign up for biology, right? We're going to dissect something. You sign up for anatomy and physiology. You're going to learn about the human body, and you do an anatomy. But then you get to this physiology, and we're back to the chemical context of life. When are we going to be over this? It's usually the most discouraging unit, sometimes seen as the hardest. I comfort in that typically I will drop a lowest test grade if we're trucking right through and getting done with all the material. But I just encourage you to hang in there. It's not that tough or as tough as it might seem at first. And it builds a lot of the foundation for understanding the physiology of the systems. Because ultimately, if you want to understand how a thing works, you got to look what's inside of it, right? Or a level below it. If you want to understand the ecosystem, you got to look at the communities and how they interact with the environment. And if you want to understand the community, you got to look at the populations of organisms, individual populations. If you want to understand a population, you have to look at the organisms and their individual needs for habitat, for water, for food, to reproduce, for territory. If you want to understand an individual's needs, you got to look at their biology inside. What are they trying to fuel? What is their metabolism? You get the idea. You always have to go one step below. And when you reduce that and you go down to it, ultimately, you're looking at a chemical context of life. And from Tylenol to cancer medication, every kind of medicine works ultimately at a cellular level. And when we say that cellular level, really, we're talking about the molecules that make up those cells. And most of those molecules exist in the context of water. So we're going to be looking at the basics of bonding, how bonds form. And to do that, we got to look at atoms first. And then we're going to end with polarity, polar molecules, and a short study of water. We're going to jump way ahead then after that, and we're going to get to the macromolecules themselves in some of the next lectures for next week. Well, I'll put one more up for this weekend, just so you don't get bored, So we're studying chemistry because biology has chemistry as its foundation. You're looking at the cell membrane right here. You have water on both sides. Those molecules are hydrophilic in one area, hydrophobic in another. This is beautiful structure and determines the function of that membrane, its ability to perform the function of separating the inside complexity of the cell from the outside chaos. So to understand how it does that, we got to look at the molecules themselves. So it comes down to the atoms. Here are the basics. Everything is made of matter. Matter is made of atoms, including us. And here are the characteristics of those subatomic particles. So making up an atom is the positive charge proton that has a mass of 1. This exists in the nucleus. Neutrons do not have a charge or a spin. They also have a mass of 1, so they're about the same size. And then they're also in the nucleus. Because of their mass of 1, if we want to know the weight of an atom, all we have to do is count the protons and the neutrons. And then electrons are in the orbital out here. We can call these energy shells. They have a negative spin on them, which means a negative charge, opposite direction, and they are a lot less than 1 mass. It's a high energy particle, constantly moving. Hard to say that they're in any one location at any given time. But we do see a blur of where they exist. So different kinds of atoms form the different kinds of elements of the periodic table. So these are organized according to the number of protons. So in a periodic table, you have the atomic number. Atomic number is the number of protons. So hydrogen is a 1. It has 1 proton. Helium has a 2. It has 2 protons. Lithium is 3. Beryllium 4. Boron 5, 6, and so off. So that you come down here to 20. Calcium, that has 20 protons inside the nucleus. Typically able to hold on to about 20 or an even number of neutrons. But that can be different, give or take 1 or 2. But we add the protons and neutrons up, and you get what's called the atomic mass. If you ever want to know just the neutrons, you take the atomic mass and subtract the atomic number, and you would have your number of neutrons. But neither of those are so important to us as far as chemistry and interactions. They do tell us what element it is and a little bit about their behavior, but not really much. What does more for how atoms interact is the electrons. But first, here's some models of atoms. So really a cloud is probably a more accurate picture because, again, we can't really see these electrons. But just like if you think of a flashlight or a cigarette end, how you can wave it back and forth and you see this orange light. You know, it's kind of like a tracer. It's kind of like that. We can never know right where the electron is, but we can see right where it's been, where it's moving. That's a little more accurate. High energy particles. High energy. They exist outside the nucleus, and these models are just models. In reality, I heard an analogy once, if you blew up the nucleus of an atom to be the size of a pea or a bumblebee, put it in the middle of the football field, say Texas Stadium, and the first electrons would be outside the stadium at the edge of the parking lot. Atoms are mostly space, not much to them. So those electrons are way out there, and that's just the first energy level. There's other energy levels where electrons exist much further out. So what you need to know is that the atomic structure determines atomic behavior. That's the story from here on up. The number of protons in an atom determines that element. So if you have the number of protons, that's the atomic number. So as you read through this, I believe we said all this already. All atoms of an element have the same chemical properties. Gold is always going to be gold. You don't cut gold, and now you have silver, cut silver, and then you get bronze. That doesn't work, right? You just have a smaller chunk of gold. And you take that gold and have a smaller chunk of gold, and you cut that gold in half, you have a smaller chunk still. Eventually, you'll get down to a particle of gold that if you spliced it, you'd be splitting the atom, and you'd no longer have gold, and you'd be dead. Probably from the energy released. So all atoms of an element have the same chemical properties. All behave the same. Properties don't change. So the ones we're interested in are about the first 20. First 20, that's up to calcium, or 25 elements are essential for life. Now, 4 of them, carbon, oxygen, hydrogen, nitrogen, chon. These make up about 96% of the living things, and the rest remain are made up by phosphorus, sulfur, calcium, potassium. Very important roles these 4 play in and of themselves, elementally and as an ion, and you'll just see where they come into play. But for time's sake, we're going to skip right through. Remember that oxygen, having an atomic number of 8, has an atomic weight of 16. So while hydrogen might be in number, the highest number of atoms in your body, this table is showing percentage of human body weight. Oxygen being heavier, even if it's in a 2-to-1 ratio, will take up about 65% of your body weight. That's not important for a test or anything, but it's just interesting information. Now, when you take an atom, we know it's defined by its atomic number, so that can't change. The moment you talk about a different atomic number, you're talking about a different element, and you go nowhere. Isotopes are the same types of atoms, except with a different number of neutrons. They're heavier or lighter, but they don't behave any differently. So they're not interesting to chemistry or within our body, but it can be used in medicine. That's my 4-minute warning here. They can be interesting in medicine. Because those nuclear reactions, the neutrons are heavier, sometimes the protons can't hold them in there, and pew, pew, and those neutrons just shoot off. We always have, generally, in the native state of an atom, equal numbers of protons and neutrons. Oh my goodness. There we go. Sorry, looking at my timer. I don't want to be too long. We're at 13 minutes here. So in the nucleus, as I said earlier, you have generally the same number of protons and neutrons, but some of the heavier elements and others, we can include more neutrons, makes it heavier, but it becomes a little less stable. And when those neutrons shoot off, we have equipment that can detect those neutrons, and we call that decay, radioactivity. And that can be used as a biological tool. It's also a hazard, which is why you want to protect yourself. Only get, tests like this or x-rays done when necessary. But bonding properties. So the effect of electrons, chemical behavior of an atom depends on its electron arrangement. This is the biggest thing. If you think about the analogy of where the nucleus is, way far away from these first electrons, and farther still from the next orbital, and farthest from that third orbital. So when any 2 atoms come together, those nuclei will never come into contact or react. The first thing to interact are going to be these electrons. And you might recall the octet rule, which says that all atoms want to have 8 electrons in their outermost shell, and they will behave in such a way as to fulfill that, whether it be giving away electrons or taking electrons, and in some cases sharing electrons, like carbon and silicon. So this one is very noble, so it behaves very well. Well, actually it doesn't. It's noble, so it's inert, right? But we look at the valence shell, and that's all we're really interested in when it comes to chemical reactions. So let's review that. Effect of electrons. Chemical behavior of an atom depends on the number of electrons in its outermost shell. So if protons equal neutrons, we count this up. We have 2 plus the 8 is 10 plus 6 is 16. So I'm going to look on a periodic table for number 16. I'm going to see it's sulfur. And I already know this one is 8, 9, 10, 11, 12. It's going to be magnesium. So we have magnesium sulfide. How would this work? Well, it's easier to pull in 2 electrons than to release these 6. And it's easier to release these 2 than to try to pull in another 6. Plus, this is a little more electronegative. So what's going to happen is these 2 would eventually transfer over here. And in so doing, it becomes a negative 2 charge because electrons have a negative charge each. So 2 negative charges are moved over here. Having lost 2 negative charges, this becomes a positive 2. So a positive 2, a negative 2, you got a match made in heaven. They're going to attract each other. We'll see this again in a little while with salt as you scroll through the PowerPoint. I'm going to go ahead and skip this part right here. Although it's slow going through it on the PowerPoint there, we'll teach you just how that periodic table is organized. What's been done is you'll see between beryllium and boron, all the transitional metals, which we're not interested in for biology or anatomy and physiology, have been removed. So we've taken the metals and the non-metals, and we've just kind of spliced them together so you could see the relationships there. So you want to hold on to things like this slide. This kind of sums it all up. They want to react to complete a partially filled outer or valence electron shell, or empty it. And this tendency drives chemical reactions. That's it. Structure dictates function. So whenever you transfer electrons, as we just said with the magnesium and the sulfur, you inherit a charge. And here we can see a better example of that. So when sodium loses that 1 electron, because it lost it, it still has the same number of protons, 11. And so it has a positive charge. And chlorine has the same number of protons, but now it's gained an extra negative charge, so it's a negative 1. And because these are oppositely charged, they will form a really nice ionic bond. So what we call charged particles are ions, right? So we have a sodium ion and we have a chlorine ion. And together, these would make an ionic bond. You can go more slowly through these slides on your own time. I just want to get through the bonds. So covalent bonds, you have 2 atoms. So we look in the case of carbon. Carbon has an atomic number of, I look at my periodic table, 6. That means 2 in the inner shell and only 4 in the outer shell. It doesn't necessarily want to let go of all 4, nor does it have the strength or electronegativity to pull in a new 4. So it chooses to share these 4. And so it can form up to 4 covalent bonds. Carbon's a beautiful element, and that's why life is somewhat dependent on it. So 2 atoms that need an electron share a pair of electrons. This is a strong bond. Those ionic bonds are simply attractions. Ionic bonds are simply attractions between atoms that have exchanged electrons. In this case, nobody's exchanging electrons. They're sharing them, and so that's a closer, tighter bond between the 2. So here's a hydrogen gas, and you can see they're close. On the last slide, they did not overlap at all between sodium and chlorine. But here you can see there's overlap of their energy shells, and that's because each hydrogen can claim both of those electrons. Double covalent bonds, stronger still. We're just talking about now 2 pair of electrons. Triple bonds, strongest still, 3 pair of electrons. So we represent that by drawing lines. Each line represents one pair of shared electrons. So oxygen, you'd have 2 lines between it because you have a double bond. Hydrogen, you would have 1 line between it because it's a single pair of electrons. And we're almost done. I think we might meet the... So here's my example of carbon that I mentioned. One atom can form covalent bonds with 2 or more other atoms. And here we have carbon, which had the 4 electrons. Therefore, it can form up to 4 covalent bonds. This is methane, natural gas in every sense of the term. The problem comes in when we have polar covalent bonds. So this is a pair of electrons that are shared, but they're not shared equally. So because oxygen, in this case, has a stronger attraction for the shared electrons, they tend to spend more time here, giving it a slightly negative charge more often than not. And hydrogen then, being a proton without its electron, gives this side of the molecule a slightly more positive charge. This resultant molecule that is overall neutral has 2 oppositely charged sides. And that's the definition of polarity. So you'd call this a polar covalent bond. And it's all due to oxygen's electronegativity. That was also an assignment, which hopefully you'll be able to do, and it'll teach you a little more about electronegativity. So hydrogen bonds occur when 2 polar molecules, such as water, come near each other, and this happens quite a lot, you can imagine. You have the positively charged hydrogen, which is always involved in a hydrogen bond, and any other atom of another polar molecule. In this case, it happens to be the oxygen of another water. This is a weak bond, weaker than the ionic bond, but very important to the processes of life and the properties of water. Okay, so we have the weak bonds, hydrogen. We have the strongest bonds, covalent bonds, and in between there, but closer to the hydrogen bond side, you have the ionic bond, and that's when electrons are transferred. Okay, well, it went a lot longer than I anticipated with 22 minutes by the time I'm actually finished. Okay, if you have questions, email me and I'll try to answer them to everybody. Have a good day.